Let's go. Well, thank you everyone for joining us tonight. We have a really exciting presentation, and most of you know me. I'm Chris Wenzel, the current president of the LIAPG, and we very much thank you for coming out. We're going to have a great presentation tonight. So first of all, as we always do, we like to thank our corporate sponsors, and we have 13 of them at 2 levels, diamond level and topaz level. And you know, our corporate sponsors are very helpful to us to keep the wheels turning, pay the bills, and you know, increase the membership and the enthusiasm here. So we've got Cascade, Laurel Environmental, PW Grosser, Alpha Analytical, Castleton Environmental, EnviroTrack, ERM, GZA, H2M, Island Pump and Tank, Nelson and Pope, Regenesis, and York Analytical. And if you go to the LIAPG website, there's a scrolling banner that if you click on the company logo, it'll take you to their website. It's just a handy little link we like to have for you. And, you know, please, you know, visit them, take some enthusiasm that they're willing to participate and do what they do to help us. So thank you. Next, this is your current board officers and board members of the LIAPG. And, you know, I want to give a shout out to this group. They do an amazing job making things happen and putting things like this together, our quarterly dinner meetings and our field trips and all that we do. You know, it's a real group effort, and they all put in an enormous amount of effort and make things happen. And I'm very proud of them. I'm very proud to be part of this group. The LIAPG is a, you know, as you saw in the disclaimer on the first page, we're an open organization. You know, anybody's welcome to come on out, participate, get involved, help us. You know, there's always room on the board for more people. We meet monthly on the first Monday of every month. The next meeting is on June 5th. And we do it online as well as in person. Generally, it's at the offices of PW Grosser. You know, we'd like to see more participation from the group. So just think about it. There's opportunities, and it's a good group of folks. We have a good time. Lastly, on this slide at the bottom here, we have a job page on our web page, and it is seriously underutilized. I know that, you know, hiring continues, but we don't see a lot of activity with people sending us job advertisements to post. And I'd like to put that out there and see maybe if we can get a few more and make it a little more robust than it currently has been in the last few months. Some information about upcoming events. We've got a lot of exciting things going on here. You know, our quarterly dinner meetings and our webinar Zooms that we do on Zoom are usually the 3rd Thursday of every month, and quarterly is obviously in the months of March, June, September, and this November or December, depending on the situation where the holidays fall. We have this webinar tonight, and then next month on June 15th, that's a Thursday, we're planning another quarterly dinner meeting. The one in March went well. The presentation is going to be about geohazard modeling for asset management and maintenance. And our presenter is going to be Dave Brogan. He's a professional engineer in a number of states you can see there. He works for Geostabilization International. They're a really good group, and he's a very interesting gentleman. I've seen his presentation. We will be submitting it to the New York State Council for PDH credit approval. It's a good one. And I think that, you know, we try and keep the webinar and the quarterly dinner meeting content varied, but interesting and relevant. And I think that this one, you'll find quite relevant and interesting. It's something that I've always wanted to see a presentation on, and I haven't had the opportunity. So beyond that, we are always seeking speakers. We have one tentatively lined up for September, and that will be a quarterly dinner meeting after the summer. And we're thinking about trying to do a multi-speaker event. We've done that in the past, and they were very successful. And the feedback that we got was very good. So we're looking to do that. Like I said, we have one speaker, and we are looking for more. And then the remainder of the year, likely for October and December. We probably won't do anything in November because of the New York State Council's Geology Days, and I'll get to that in a second. We have 2 field trips planned for the summer. In July, we've got on July 15th, and that's a Saturday, we've got the summer canoe kayak trip and picnic, and that's going to be again at on the Nissaquag River in Smithtown, and the picnic will be at the takeout point in Nissaquag River State Park. It will be, hopefully we'll have a pavilion again like we did last year. It will be catered. It was very nice last year, and it will be very inexpensive. The council, the LIAPG will foot most of the bill for it. So, you know, if you are interested in doing something like that, you should come out. And if you're not a water person, that's okay. Come to the picnic anyway and see us all and hang out with us. You know, I think the start time for the canoeing is around 10:30, 11 in the morning. It's about a 2.5, 3-hour trip tops. So that puts the picnic square in, you know, right after lunchtime in the afternoon. And we're planning for good weather. So that's the canoe trip. And then the next month on Sunday, August 13th, we're going to do the Museum of Natural History guided tour again, which was a real success last year. We had a guided tour in the Hall of Gems and Minerals. Probably a lot of people on this call have heard me say this before, but you know, it was a great day. You get in right when the museum opens, so it's not crowded. And, you know, the Hall of Gems and Minerals had been redone. And I think that personally, I think the museum did a fantastic job of organizing the entire area and the minerals, you know, by geochemistry, as well as the specimens there are world class. They are outstanding. So if that's something that interests you, you know, watch for the announcements to sign up, and you know, we're going to have a good time. So moving on, there's another event here we wanted to talk about briefly. Central New York Association of Professional Geologists, they're upstate, but they've got a save the date flyer out there for October 6th, and they're doing a geology field day that they've done in the past. And it's going to be a whole day. They'll have drilling demonstrations and aerial drones and a lot of other interesting things mostly in the environmental arena. But you know, it can be very educational. And again, you know, October is a nice time of year. If you come on out, probably going to be a nice day, and it might be worth the trip. Even if we're down here on the island, you could combine it with some other activity and you know, have a good time. You can find out more at their website there on the bottom. Sure everybody can find it. And then in November, the New York State Council of Professional Geologists is having the 2nd annual Geology Days conference. And that's going to be again in Saratoga Springs, November 13th through the 15th. And the turnout last year was about 240 people. And it was 2 days of lectures and presentations. And the content was wonderful. The people had a good time. And, you know, if you have a PG and you're trying to keep up with your professional development credit hour requirements, this is a great place to pick up 8, 10, 12 or more. So watch for the further announcements when the registration opens for it. I have a feeling that it will go fast and probably be filled to capacity. I have seen, you know, as a board member on the council, I have seen the lineup of presentations. It's going to be a good one. And lastly, I'll just say that, you know, the sponsorships are open and there are varied levels. And you can go to the New York State Council's website right there at the bottom, find out more about it. If your company is, or you are interested in sponsoring a bar or just being a sponsor or having a table there, you know, check it out. It's going to be a good time. Almost done here. Just wanted to talk briefly about our other sister organizations. I've mentioned the council array there at the top, and then across New York State, we've got 4 other, you know, parochial organizations, the Buffalo Association, Central New York, I mentioned already, Hudson Mohawk Valley Professional Geologists, and then we have the Northeast chapter of the American Institute of Professional Geologists, and the Pennsylvania Council of Professional Geologists is obviously they're in Pennsylvania, but you know, all these associations have dinner meetings and webinars and lectures. I failed to mention that the Central New York Field Day thing in October is being also sponsored by the Northeast American Institute of Professional Geologists. And you know, if you look at the Pennsylvania website, they always have a robust program of lectures and things that are really interesting. A lot of fractured rock stuff, but there's one thing there. If you are working towards passing both parts of your ASBOG exam, they're putting on, starting in July, a 6-part webinar series for ASBOG exam prep. And it is a couple $100, but you know, I haven't taken it, but I have a feeling that they're not messing around and it's probably a good course. So if that interests you, check it out. You know, there are probably a few people on this call that are registered or in the process of registering for the fall exam series. And lastly, I'll just say that, you know, Stony Brook University, you know, near here, has a geology open night lecture series. And I didn't see anything on there today because we're pretty much at end of semester, but they have, you know, usually a fall and a spring lecture series. And those topics also are very interesting. They're done both by, you know, grad students there, as well as professors that are working in a large variety of different areas of study. So just, you know, there's a lot of content out there, and you know, we want to make sure you're aware of it, that we're not the only one stop here. There's a lot more out there. So with that, let me get to our main event. And the presentation tonight is by Dr. Carol Finn of the United States Geological Survey in Denver. And the presentation is the geophysical mapping of Yellowstone's hydrothermal plumbing system. And this is a good one. A real good one. You know, you can see in the picture there, it's cool. They had a helicopter. I just want to say a few words about the ground rules here. If you're looking for PDH credit, we are obligated to certify and document your participation, and, you know, by the state education department through the New York State Council. So if you are doing that, we need everybody to use the chat function. First and foremost, if you're appearing in the chat and your name isn't obvious, like you're coming up as iPhone or iPad or something else, we need you to identify yourself in the chat window and say, it's me, so-and-so, I'm here. Secondarily, as we go through the presentation, Dr. Finn has quiz questions that are embedded into it. So you need to be present, you need to be paying attention, and you need to answer the multiple choice questions. Nobody's going to grade you. If you get it wrong, okay, fine. But we need to know you're there. You know, the state education department has made it clear to us that we need to do a better job of documenting this and ensuring that people are present and accounted for and paying attention so that they're getting the content and actually getting the credit due them. So if you could do that, we would very much appreciate it. It makes my life and other board members' lives easier in processing and producing the PDH certificates that we issue. And lastly, on that topic, I'll say, please be patient. It usually takes us 1-2 weeks to get them out. We will get them to you. If you don't see them after 2 weeks, send an email and say, hey, did you issue them? Because I didn't get it. And there have been instances where if you're using your company email, the LIAPG email with the certificate, because it's an attachment, may get caught up in the security filtering on the server, and it may come through slowly, or it might not come through at all. I've dealt with several of those in the last week, a couple today actually. But you know, again, you know, we're trying to do the best job we can, and be patient with us and support us. With that, I'm going to stop talking. I'm going to stop sharing my screen. I'm going to let Dr. Finn take over and drive here, and she'll share her screen. So thank you for your time.
Thanks for that introduction, and thanks everyone for being here. See, I'm going to share my screen. Can everybody see that?
Yes.
Okay,
Yep.
Great, thanks. So the title of this talk, as you can see, is Geophysical Mapping of Yellowstone's Hydrothermal Plumbing System. And we're doing that. There's a variety of geophysical methods that have been used in Yellowstone, but the one we're using will employ this helicopter with a very large hoop, which I'll be talking about. The surveys were flown in late December of 2016, and we got the data about 6 months later and wrote a paper that came out in Nature a little over a year ago. And they got some news coverage, so you can always find the easier to read version of it online someplace. So Yellowstone sits, this is a geologic map of Yellowstone. It's in Wyoming. The oldest rocks in the area are Precambrian to Paleocene sedimentary and metamorphic basement, which crops out in the northern part of the park and in the southern part of the park. There are also tertiary volcanics that are shown here in this light brown color. About 630,000 years ago, the caldera, which is outlined here in gray. Can everybody mute? Because I can hear somebody.
Yeah, sorry, Dr. Finn, I'll stay on people, getting them to mute.
Okay, thanks. So the caldera formed about 630,000 years ago with the eruption of the lava creek tuff, which are shown here in green. And after that, there were, up until about 70,000 years ago, rhyolites erupted within the caldera and a little bit out to the southwest of the caldera. And this is the inner ring fracture zone. And I'll talk about these lines later. This is Yellowstone Lake. And the other thing about the park that's important to know with regard to the hydrothermal system is there's a lot of faults. There were faults during the Pennsylvania severe orogeny, faulting during the Laramide orogeny in the Cretaceous, and there's active faulting due to basin and range activity now. So faults shown in brown are an important component to the hydrothermal system. And this is part of the Teton Fault, for example, and it continues underneath the caldera somewhere. Okay, what do we know about Yellowstone? This is a summary image based on geophysical and geochemical data that at the lower crust, there's basaltic magmas. A lot of people think there's a mantle plume here causing the high temperatures. And the basalts rise, silicic melts get extracted, and there's a zone of rhyolite partial melt in the shallow part of the crust underneath Yellowstone. The caldera boundaries are here, and what the ideas up until our study was that you can get fluids exsolving from the partial melt. There are fluids that also come in from the surface, and they go along the caldera boundary. So the idea is that you've got fluid flow along the caldera boundary, and then it goes horizontally to create the geysers and hot springs and other hydrothermal features you see in the park. These red dots are showing earthquakes. There's earthquake swarms often along pre-existing faults that suggest fluid motion. How do we know that it's hot under there? One data set that's been used, seismic tomography data. The triangles are stations, and the seismic low velocities, which are shown here in red, indicate pockets of magma, hot rock, and these are depth slices at 2 kilometers. You don't see much of it. You see evidence for low velocities around the park. Some of these are not well constrained. These might be related to hydrothermal fluids, CO2 gases. But as you get to about 5 kilometers depth, You see these low velocities in the central part of the caldera, as indicated by the black line here. And at 8 kilometers, but it starts to go away at 14. So it's really in the very upper crust that we see this evidence from the seismic data for hot rock. What do we know about the hydrothermal system? Well, what we know about the hydrothermal system is largely from geochemical data, from hydrothermal fluids, from rivers, from gases. And this is one of the pictures of how the hydrothermal system works. There's a lot of precipitation. That's one of the factors that you need to have the hydrothermal system. Hydro means water, so you need a lot of water, and there's a lot of it, lots of snow in particular in Yellowstone. And you need a way for the water to get into several kilometers down to start interacting with the heat source. And those are the faults that we saw on the geologic map. So there's a lot of faults, so the precipitation can go along faults, which are also required for the hydrothermal system to depth. Well, you need a way to heat up the system, and I showed you that image in the previous slide of where the hot rocks are, and there's a lot of gases exhaling off of this magma chamber. The fluids interact with the gases, they also interact with the rocks. They change chemistry, so the fluids no longer look like cold groundwater as what went in. These fluids can go into the low elevation areas, places like Old Faithful. And so you actually see liquid phase hydrothermal fluids here, but at higher elevations, the fluids are too dense to get to the surface. So you basically just have gas getting to the surface. And so the chemistry of the fluids, and this comes in to be important later, is quite different from the higher elevation areas where you've got gas interacting with groundwater. And the fourth element you would need for this hydrothermal system, you saw in the previous summary slide that the idea is that fluids move laterally as well, which I'm just showing with these blue arrows. And so you need some pathways for the fluids to go. And the boundaries between lava flows, and Yellowstone consists of stacks of lava flows, are brecciated, meaning they're kind of rubbly and disrupted, and fluids can go in the boundaries between lava flows. So we've got precipitation, faulting, heat source, and horizontal pathways. One of the things missing from this picture is the pathways, where really is the water going? And that's what our study is for, is to identify those. Okay, we have the first quiz questions. So the first one is, what factors are necessary to produce Yellowstone's iconic hydrothermal features? Multiple choice. Well, it should be 1, 2, 3, and 4. I'll let you read that. And then what kinds of data were used to infer Yellowstone's magmatic and hydrothermal systems previously? MRIs, 2, borehole temperatures, geologic mapping, seismic data, and geochemistry. 3, ground penetrating radar, gravity data, and geologic mapping, or all of the above. Okay, I'll go on. I'm not monitoring the chat, so I figure it's okay. Okay, what tools do we use? This is a close-up of a helicopter with the instrument. There's a generator at the top. There's a receiver. This giant loop, 25 meters, is what's called a transmitter coil. There are receiver coils, pitch and roll sensors to monitor the movement of this transmitter coils, laser altimeter for the elevations, GPS. There's also another instrument called the magnetometer. So this whole instrument is an airborne time domain electromagnetic system. So this is an electromagnetic system, and this is a magnetometer. How do they work? This is an instrument called SkyTem. There are other companies that have similar instruments, not very many. So what happens is the generator powers an electric current in the loop, in the transmitter loop. Then the transmitter coil generates a magnetic field. This is Faraday's law. It's a basic law of physics. So that magnetic field, this indicated by these white lines, generates currents in the ground, also part of Faraday law. And these currents are in a loop, just like this loop, and they generate a secondary magnetic field, which is sensed by the receiver on the hoop. And the properties of the secondary magnetic field and the difference with the primary field tell us about the electrical resistivity of the ground. So the currents are stronger in clays, groundwater, and thermal fluids than in things like dry lava flows. So the other instrument, the magnetometer, measures the entire Earth's magnetic field and is a way to differentiate magnetic rocks like volcanic rocks from sedimentary rocks, but also it can tell differences, can identify isolated lava flows, dikes, intrusions, and faults, as well as clays, because the clays are not very magnetic. How does it work? And specifically, the helicopter flies back and forth like mowing the lawn at a low altitude. And this is just pictures of the transmitter current and then what the signals look like received back in the loop. You don't need to know this, but we do a process called inversion, where we take all of this data and translate it into resistivity with depth. This is depth, this is electrical resistivity, and we get these one-dimensional called soundings, one-dimensional layers that we all stitch together to make cross-sections and three-dimensional models. So where did we fly? All of these lines on here show where we flew. This is Norris, the Norris Mammoth Corridor. This over the northern part of Yellowstone Lake. This is the Sour Creek Dome. We flew mostly around it. This is the Mallard Lake Dome. This is Upper Geyser Basin, Lower Geyser Basin, so Old Faithful, Grand Prismatic Hot Springs, and then some long lines across the caldera. So these are some of the parameters of the survey. The loop was supposed to be 30 meters off the ground. Sometimes it had to be higher for a variety of reasons. We had a variety of line spacing. This is about 400-meter line spacing. These are 250 meters. This is a pretty good survey, a pretty big survey, at least from ones that I've flown. Okay, so now I'm going to stop sharing this screen. I'm going to show you a video of Skytown flying because it's pretty cool. Screen. Can everybody see it?
Not yet.
How about now?
No.
Okay, let's see. Share screen.
Okay, we can see it now.
Okay. All right, this is just an image of with some jazzy music of Skytown flying in Reunion Island and over a very big volcano. But you can see how big it is. This is this is very similar. I mean, this is more rugged than Yellowstone, flying over the volcanics along prescribed lines. The pilot has a map. They fly along flight lines. There's the magnetometer, the generator, the cones. They really try to maintain the elevation. So they had trees, so they have to fly higher, but pretty close to the trees. Like at Yellowstone, we did this as well. And they tried to maintain a constant different distance from the ground. And this is amazing that they're able to do this and this steep topography. So that was done by the French. Am I back to the presentation? Okay. Well, can everybody see this?
Yes.
Okay. So, all right, what can we resolve with this system? All systems have limitations on the size of features that can be resolved. So the way, depending on the elevation, but generally speaking, there's a broad footprint for the time domain system, that big loop. And it's about 100 meters. So we can't It can be 50 to 100, but it depends on the elevation. But mostly we can't resolve features that are smaller than 100 meters in diameter. So it's kind of like we're looking at the plumbing system of Yellowstone. So a good analogy is a city's water distribution system. There's no pipes in Yellowstone for the hot water, but think of the lava flow boundaries as the pipes. So we can image the scale of the pipes of the water distribution system. So I can probably see the pipe coming into your house, but I couldn't tell the difference because of the resolution limitations between the pipe going into your kitchen and your bathroom. What that means is I can't resolve the little 20-meter wide conduits for specific geysers or some specific hydrothermal feature, but we can look at the whole system. In terms of depth, we generally can image at shallow levels, sometimes 4 meters thickness. So if you have a body that's only 1 meter thick, we're not going to see it. And then that depth resolution decays at depth. So maybe 10 to 20 meters at the surface and getting to be 25 to 30 at depth. And the depth that we can see with this EM system is 500 meters, 700 meters, something like that. Okay, more quiz questions. What geophysical instruments were used in this survey? Gravity meters, radiometers, and magnetometers. 2, seismic geophones and ground-based time domain electromagnetic data, time domain electromagnetic instruments, and magnetometer. All of the above. How were the data collected? 1, on the ground. 2, from the air with an airplane flying scattered lines. 3, from the air with a helicopter flying along prescribed mostly uniform lines. Or 4, all of the above. Okay, I'll move on. Somebody can yell if they want me to stay. All right, so we collect this data, we measure resistivity. What does that tell us? So dry volcanic rocks are electrically resistive. We know this from lab studies and from surveys in other areas. And the numbers that we use kind of vary from system to system and from area to area. In Yellowstone, rocks that are greater than about 400 ohm meters resistivity are kind of typical of dry volcanic rocks, and they're magnetic. They're not super magnetic in Yellowstone because they're rhyolites. Basalts tend to be more magnetic, but they are magnetic. And on the images I'll show you, these kind of match the colors. So dry volcanic rocks are going to be this color. If you add water to volcanic rocks, it drastically decreases the resistivities. So from hundreds to thousands of ohm meters to maybe 50 to 300 ohm meters. And adding water does not change anything about the magnetic signal. It's still magnetic. And what this signal would look like, shown in green and yellow colors, are mostly fresh volcanic rocks and groundwater. And if there are thermal fluids with low pH, then those resistivities are lower than the groundwater. Where you have hydrothermal alteration, that's where hot fluids are coming to the surface or hot gases. They alter the volcanic rocks to clays, and those are very low resistivity. And you add water, they can be 1 to 2 ohm meters, and it destroys the magnetic signal. So you have a very big difference between fairly magnetic rocks that are not altered and hydrothermally altered volcanic rocks. This is in Norris, by the way, Hot Springs. This is a graph showing porosity, fluid conductivity, and the colors are indicating electrical resistivity. And we use these kind of pictures to try to tell a little bit more about what our models, which you'll be seeing, are showing. So we know fluid conductivities are measured in a lot of places in Yellowstone. Porosities are measured in a few places. They're not very well known, but I can, from that information, the porosities of various kinds of units, and the fluid conductivities at this level are pretty typically groundwater. Anything at about 200 microsiemens per centimeter and less is going to be non-thermal water, i.e. groundwater. And values greater than about 1,000, 1,500 are likely to be thermal water. This is very general, but it's a way for us to look at our data and get ideas about if we see values here, like 30 to 100 ohm meters. We also have some information about the porosities as well. And we see that the these lower resistivities can be related to higher porosities, which makes sense because you can have more water in the system. And as I mentioned, water drastically reduces the resistivity of rocks, and so does pH, and so do salts, which you can get. It's not salty water at all. The thermal fluids are not salty, but they can have low pH. So this is a way for us to tell the difference between thermal fluids and groundwater. All right. The other thing that we used in Yellowstone to try to understand our data and our models were analogs from other places. So in Taupo, New Zealand, there's a lot of geothermal exploration. So they have really deep boreholes, like several thousand meter deep boreholes. And they've characterized the hydrothermal system at the shallow level. It is a shallow aquifer. So this meteoric water. You've got a hot region in here. It's been drilled into. There are hot fluids and gases coming from this region. And in this area above where the fluids are coming up is hydrothermally altered and hot. And the water in here are thermal fluids as opposed to shallow meteoric water. This is the kind of thing we're going to be looking for. Well, how do they know this? Besides the boreholes, they use a method called magnetotellurics, which is also generates electrical resistivity models. It's very coarse, sees deep. But the point is that you can see in these red colors, this is from Iceland. We're going to have the opposite color scale, so I won't remind you of that. But theirs is to try to show regions that might be hot, but these are clays, and clays form above the hot regions of interest for geothermal exploration. So they're indicators for upflow of systems. So there's probably faults and fractures directly beneath these kinds of electrically conductive features that tend to be in the upper, 1 to 5 kilometers. This is from Coso in California. The upper, and these reds here are also clays. They're 500 meters thick. That's a kind of a typical number, and extend across the region for tens of kilometers. So you can see the scale. And they're sitting above a resistive region, which is actually what the reservoir is, the geothermal reservoir. Well, we are just collecting, when I did this slide, we didn't have any of this kind of data at Yellowstone, and we do now, but it hasn't been completely analyzed yet, and we are seeing this kind of feature. But for this study, we used the magnetic data. The clays are less magnetic than the volcanic rocks. So this is a magnetic map from Taupo, New Zealand, showing a big broad, the blue colors are magnetic lows, and these are indicating these hydrothermally altered clays that are showing up in these kinds of places above the hydrothermal reservoir. So if you see this kind of feature, then we can presume most likely that there's water coming directly above, beneath that hot water, so that these are indicators of upflow zones of hot fluids. Okay. Questions? What rock and fluid properties are important to understand the models of the electromagnetic and magnetic data? 1, electrical resistivity and magnetic susceptibility. 2, density and seismic velocity. 3, viscosity and permeability. 4, all of the above. Okay, so I'm going to show you a bunch of cross sections from our data, from our models, and they're going to all look like this. This is from Norris. So the flight line map is here, the cross section is here, and Norris Hot Springs. Geologic map, this is a magnetic anomaly map. So it's a plan view, and this is a cross section along this red line. And as I said, the pictures are going to look the same from here. So I'll go into detail in this one. This one goes across Lava Creek Tuff, which is the green colors. The gray indicates altered areas. So these have lots of plays. These are boreholes. Here's the location of the profile. If you look at the magnetic data, outside of the gray areas, you generally see magnetic highs, which is what we expect over unaltered, fresh volcanic rocks. And you see these blue colors indicate magnetic lows, and these are all the same rocks that went across here. So the difference is that these have been hydrothermally altered. So that changes the magnetic signature quite a bit. This figure is a cross-section from our resistivity model and a magnetic susceptibility model. So above this black line is the resistivity model, and below the black line is a susceptibility model. Obviously very different units, but I was just trying to make it look more like a cartoon to explain the geology of the area rather than talk too much about the specifics of the geophysics. And this is a kind of a blurry model. The susceptibilities are not well constrained. It just gives you a broad indication of what's happening. So on the west side and the east side, you see both high resistivities and high magnetizations. If you remember, these are dry volcanic rocks. But within the dry volcanic rocks, you see not some lower resistivities here and over here. And this is the boundary between Lava Creek Tuff A, which came out first, and Lava Creek Tuff B. And it's likely to be a brecciated boundary. We know it's the boundary because there are two boreholes in the area. So where the boundary shows up in the boreholes, we can extend it into the resistivity model here. So this is, these resistivities are very coincident with cold meteoric water. How do we know? Well, some of these layers come out at the surface as cold springs. So we have a really some good constraints on this part of the model that and this is a good example of where you can see the groundwater. It's in the upper 50 meters or so. In Norris Geyser Basin, it looks quite different. Once again, you see the susceptibilities, these low values. These are indicating a clay cap. There's boiling. There's hot fluids coming and gases coming up along fractures. These are mapped faults shown here in brown. So it's coming up along fractures, and it is altering the rocks. You can see some blebs of moderate resistivity, lower resistivities, and you can really see the disruption of the Lava Creek Tuff by the hydrothermal system and the resistivity and susceptibility models. If they weren't there, this would just look like a continuous reddish layer. So this is am I really seeing actual faults and fractures in these breaks between higher and low resistivity? No, it's just an indication that the whole units are broken up and that fluids have come in and altered the rocks. This is a picture of Norris. All right, so this is from Yellowstone Lake. Yellowstone Lake has the highest heat flow in the park. This is the geologic map. Lava Creek Tuff, tertiary volcanics, some post-caldera rhyolites that probably go out to the middle of the lake. These red triangles are vent locations for fluids. They're all over the place. They're fissures. This is the magnetic anomaly map. These should be relatively high values going across here, and it's not. It's also been very hydrothermally altered. Here's once again, the resistivity cross section above the black line and the susceptibility model below the black line. The lake is very electrically conductive, and these systems like to find conductors. So when they do, they don't penetrate as deeply as places that are not so electrically conductive. So you'll see variations in the thickness of the resistivity model because of that. You see a lava flow, once again, the same thing we saw in Norris, some higher resistivities, probably indicating boundaries between different lava flows. This is a way that we can map, by the way, lava flow thicknesses is with this data. But as soon as we get into the lake, we just see these very low resistivities reflecting thick hydrothermally altered clays. There are mapped, these are fissures, so that's what these brown lines indicate. And you see just what we expect, low susceptibilities indicating vertical flow of fluids along these faults. These stars indicate general locations of seismic swarms that are interpreted to reflect fluid movement. So we have a lot of constraints that suggest that yes, we are seeing the pathways for vertical fluids coming up and then how they go horizontally beneath Yellowstone Lake. And this is the lake water, by the way. It's very cold and very fresh. So it's pretty resistant. This is a profile across Old Faithful. So all these pinks are post-caldera rhyolites. This is a dome. These are boreholes. The magnetic data are pretty mottled looking. I won't talk too much about it, except for these blue areas here are also places that are altered. This is the entire basin. It is hydrothermally altered, but it's covered by younger sediments. So you can't always see the clays. There are some boreholes also. These are all from the 60s, by the way. The park would never let you drill into these features now. So this is a really good cross-section because it shows some important features. You see this really resistive lava flow. It looks very thick. Most lava flows this would be 400 meters, are not this thick. There's probably another lava flow here, but didn't have a boundary along which water could flow. We get into firehole meadows up here, and things start to change. You really start seeing evidence of breaks in a higher resistivity body under here, some lava flow, lower resistivities that look like thermal fluids. And then we have another lava flow as we go southeast towards Old Faithful. Once again, you see this somewhat moderate resistivity boundary here. You see it southeast of Old Faithful as well. And once again, we interpret this to be meteoric water flowing along lava flow boundaries, or there can be intra-flow boundaries. But then you see some lower resistivities that are more commensurate with thermal fluids. Now, Firehole Meadows was not supposed to be a thermal area. And from this data and from the mag data that shows that there's clays suggesting to the south, I thought, gosh, it really looks just like these areas. Is it a thermal area? And sent some of my colleagues there last summer, and sure enough, they found some thermal features. It's a snow-free zone in the winter. So these data sets can be used to help guide people to look for new thermal areas. But if we go into the basin, the Upper Geyser Basin, we see something similar to Norris, where you see these lava flows, which by all rights should maintain their purplish character in the geyser basins, being very disrupted because there are hot fluids flowing up from depth along buried faults and fractures, and really quite altering the rocks. These resistivities are lower than Norris, so they're probably there's more pathways here in Norris. There's just mostly fracture permeability in the lava creek tuff. So most of the alterations occurring along fractures, but you can see it's occurring along different lava flows. And from the geologic perspective, and from that first image that I showed you with the magmatic system, the rhyolites and the basalts, people thought when you stand here, you can see water coming out of the boundaries between these lava flows. So they thought that the fluids were coming up along the edges of the caldera, or maybe in a couple places, but mostly are laterally flowing. This is a case where we see that there's probably fluids coming up along Firehole Meadows and going into the Upper Geyser Basin, but there really aren't very many other examples of this. Mostly what we see is evidence for vertical flows of fluids beneath the geyser basins. In the susceptibility data, the magnetic susceptibility model, we see some lows here and here. We don't know whether they're fossil hydrothermal systems, clays, or current day hydrothermal systems, and we don't have the resolution to see hot water. They're too deep for the resistivity, but it is possible that these are old systems, and we can't tell the difference between old ones and active ones in the magnetic data. Same kind of picture. This is north-south across the caldera. And once again, big lava flow in the southern part of the caldera with moderate resistivities showing groundwater going at shallow levels. It's generally within the upper 100 meters. And then you see all of these lower resistivities all along here, which suggest thermal fluids. You can see evidence for water, low susceptibility clays, indicating vertical flow of water. It's hard to say whether these geyser, it looks like the geyser basins are connected at depth. Their systems, probably water coming up here, flowing out here, water coming up here, flowing out here. So there is connectivity. It seems like there's connectivity between the geyser systems in this north-south line here. Here's the caldera boundary. You can really see it's faulted with water flowing along it. And this profile goes from southwest to northeast. So mostly across post-caldera rhyolites. Here's Lava Creek Tuff. This is the Sour Creek Dome. This is an older flow, 300,000 years. And then we get into the tertiary volcanics. The magnetic map is pretty modeled. I won't talk too much about it. It does highlight a lot of the altered basins though. But the electrical, the resistivity and susceptibility model cross sections are pretty interesting here. I'm going to talk more later about Smoke Jumper Hot Spring. It's at high elevations, and you can see in the susceptibility model, a susceptibility low, indicating clays. And hold on. It just came home. He's yelling at his friends. So what's happening here is this is high elevation. So the fluids are boiling here and gases are coming up to the surface along fissures. And I'll talk about that a little bit. But what you see is low resistivities here and increasing towards upper geyser basin. And as I said, I'll talk about that a little bit more. And then as you go across, this is where Old Faithful is, you see the meteoric water in the Mallard Lake Dome and some thermal fluids. But really across the central portion of the caldera, you don't see evidence for hydrothermal activity, either in the electrical resistivity models or in the susceptibilities. They're nothing particularly low until you get over to Mud Volcano on the edges of Sour Creek Dome, where you've got, these are very acidic hot springs and lots of clay alteration, and they're on both sides of this dome. And then the tertiary volcanics are resistive at the surface, but not at depth. So this is an important observation that that there just doesn't seem to be a lot of hydrothermal activity in the middle of the caldera. Okay, so I'm going to show you some depth sections now. We saw some cross sections across our resistivity models. Now I'm going to show you some depth sections. So this is at 10 to 15 meters depth on top of the geologic map. You see mostly it's these higher resistivities, not surprising. You're in the upper parts of the system, dry volcanic rocks, so we've got your basins. Geyser basins, you've got lower resistivities, and over here, there's a lot of hydrothermal alteration. As you get very deep, though, you see a very different picture. You start seeing these very low resistivities indicating fault boundaries and water flow. And so the whole hydrothermal system is very clear. In Yellowstone Lake, you see these linear features that suggest faults, and there's a lot of faults over here and linear features. Here. Okay. This is another picture. This is showing the resistivities at depth and where I think are upflow zones. So these are the lowest resistivities, which you see in this dark blue, and outflow zones. We don't know exactly what directions the water is flowing. But one of the things you don't see is it in the middle of the caldera. We have a few lines. It's very resistive. I go back to the previous one. You see that there is mostly higher resistivities all within the central portion of the caldera. These brown blobs are showing locations of the magnetic, those low magnetic susceptibility areas, and this at a depth of about 1,000 meters. And these are showing the areas where we think are these clays that indicate vertical flow of fluids beneath them. And this picture here is at greater than 1,000 meters depth. This orange here indicates the outline of the seismically determined magma chamber. And there's also low velocities here in Norris. So there's a lot of correlation between where there's the heat source and faults and these clay layers. The faults are once again are in brown. These purple lines, you can determine edges that might be faults from the magnetic data, and those are on here. So there's a lot of correlation between where the clays are and where there's faults. And there just isn't much in the central part of the caldera. And this is a pretty different view than what people thought previously. They thought that a couple things is that mostly the fluids were coming along. Some people thought the fluids were coming along the caldera boundaries and then flowing laterally. What we show is that we've got a lot of places where the fluids are coming up vertically along faults. People also had surmised that the hydrothermal system would extend kind of in this, would be not uniform, but more extensive underneath the younger lava flows than we see in the central part of the caldera. Okay, I think these are the work quiz questions. What do the resistivity models tell us about Yellowstone's hydrothermal system? 1, they image magma. 2, they image shallow pathways for groundwater and thermal fluids. 3, they image deep magmatic brines, or all of the above. Second question is, what do the susceptibility models tell us about Yellowstone's hydrothermal system? They image faults in clay caps that overlie fault fracture conduits for thermal fluids. 2, they image magma. 3, they image shallow groundwater, or 4, all of the above. Okay. So that's the generally big picture for some of the things that we learned about Yellowstone from our models. Is there's shallow groundwater. We see how it goes into the hydrothermal, into the basins. We see thermal fluids. We see the pathways for those thermal fluids. Groundwater modelers can use these models to actually get a better idea of how the water is, what directions the water is really flowing. And I wanted to just talk a little bit about how we can link our models to understanding factors that control microbial biodiversity. That seems crazy because we're looking at tens of meters of scale as opposed to these little teeny organisms, but there is a link. So certain springs in the park are very elevated in methane and CO2, and they're shown, and also in hydrogen, shown by these big circles. And Washburn Hot Springs and Hot Spring Basin and Smoke Jumper Hot Spring, they're very notable compared to other springs like in Norris and Old Faithful. Once again, this is the picture that I showed earlier. And it turns out that the conditions where you've got high altitude hot springs, so that remember that's just gas, mixes of gas and meteoric water, is very conducive to growth of organisms, more than what you see with liquid hydrothermal fluids. This is like Old Faithful versus Smoke Jumper Hot Spring is higher in methane, helium, and H2, and lower in chlorides and sulfates. So here's a picture of that. These are chlorides versus SO4. And the hot springs I was just talking about, Smoke Jumper and Washburn, have no liquid phase at all. It's just a complete mix of gases and meteoric water. And it turns out that these springs have incredible biodiversity. So these represent evolutionary relationships among organisms. I'm not a biologist, so I don't completely understand them, but basically here's the original organism and here's how they diversify. The colors aren't so important, but what's important in both of this is phylogenetic trees for archaea, and this is for bacteria, is the tremendous amount of diversity there is. And in fact, Smoke Jumper Hot Spring, which is hardly, it's just a puddle, comprises 50% of all known major lineages of life. So, which is spectacular. And the variety of microorganisms are supported by this mixing of gas and meteoric water. And it creates hydrogen, and that's what they like to have for lunch, is hydrogen. Here's another picture of the same kind of thing, where this is biodiversity, and you can see this is kind of what most of Yellowstone looks like, except for Smoke Jumper and Washburn. And as you see in this picture, here's biodiversity going up, and this is more gas in this direction. So it's basically saying these places where you've just got gas and meteoric water are really conducive to generating large communities of various organisms. And then also the organisms also oxidize the sulfur, which leads to acidification of waters and also leads to hydrothermal alteration. So there's a lot of interaction between the geology and the microbial community. Oops, what does that say? So Smoke Jumper sits on top of a post-rhyolite lava flow. The gray indicates alteration. There's a mapped fissure here. Here's the magnetic data. Here's a magnetic low associated with the alteration, and it's pretty straight. So this is the fissure. But this picture really illustrates, I talked about it a little bit before, the susceptibility model shows these low susceptibilities indicating clays and the source of gases, which are coming up through a fissure. And you see these moderate resistivities, which are reflecting gas dissolved in meteoric water. So they're moderate resistivities. As you go away from the source of the gases, the resistivities increase back to levels that are typical for meteoric water. So this really shows the process of, that we know that this is an indicator of gas, and there's a fissure, and the resistivities tell us the story that these are the influence of the gases out to several kilometers until the gas is no longer dissolved in the meteoric water. So this is that picture that I keep showing you. So before, we didn't have any idea of what the pathways were for the various fluids and gases, and now we do. Here's the blues and greens colors here show where these fluids are, where they're coming into the system. And this is the summary of the talk. So our models show, they provide the very first high-resolution, large-scale view of groundwater pathways in the upper 500 meters of any hydrothermal system globally. No one has done a survey this big. There's been some small ground surveys. So this was the first, and hopefully people will do more. The magnetic models can image potentially steeply dipping pathways for groundwater. I didn't talk too much about that below 500 meters depth, but really shows the clay caps above upflow zones. And remember that the boundaries between the lava flows provide permeable pathways for groundwater. And it's this combination of regional basin and range faults, the caldera boundary, the inner ring fracture, and faults associated with resurgent domes are allowing the flow of hot hydrothermal fluids to come up shallow to the surface. Once again, we can see the cold meteoric water that flows into Norris Basin, and it matches the geochemistry really well in Norris. It mixes with deep thermal fluids at the edge. And so they're warm springs. It's the only place that we really have seen that. It might be the only place where people have looked. And although mixing of this kind of shallow meteoric water and deep thermal water seems to be negligible for most of the rest of the thermal features, there are clear pathways for lateral groundwater flow into the basins. We saw that in Old Faithful, where you see this meteoric water coming into the basins, and they may just be coming in deeper than at Norris. And the biodiversity in the springs relates to the chemistry of the springs and structures that bring thermal fluids and gases to the surface. Here's the last quiz question. How is this study added to understanding of Yellowstone? 1, it will help identify locations of potential biodiverse springs. 2, it provides the first images of the pathways for Yellowstone's regional hydrothermal plumbing system. 3, shows that most thermal features like geysers, hot springs, hot pots lie above fractures and are faults that allow thermal fluids to rise to the surface, or all of the above. And I think I will stop there and ask for questions.
That was great, Dr. Finn. Thank you. If anybody has questions, feel free to unmute yourself and start asking away. You can also turn your video feeds back on, or if you prefer to put your questions in the chat, I will read them out.
Hello, Dr. Finn.
Hello.
Hi, Mike Teeling here. Very interesting talk. It was, I want to acknowledge my sincere appreciation for the topic matter. I want to also ask the question, and you already preliminarily have answered it. Yeah, I'm curious about the progress or the strategic pathways forward to performing more studies like this to begin assessing this data across that temporal nature, from year to year or from 5 years to 5 years, and what that data would eventually would look like. But can you provide any more insights as to what future studies may in fact be planned, or is it just really sort of out there and maybe it'll happen or maybe it won't?
These surveys are kind of expensive up front, so people don't tend to do repeat surveys. I mean, it will be important with climate change. I mean, I think that is a huge, if things dry up, there's not going to be a source of water. So it would be interesting to do them if the climate changes. There are places like the Everglades where these kind of surveys were flown to look at the movement of the freshwater saltwater interface. Yeah. And I think they're repeating those. But generally speaking, not that many people seem to be able to do them, not just from the financial perspective, but just being able to, the modeling of the data is pretty complex. I don't do it. I have other people do it. And so a lot of the people that fly these surveys are for industry, for mineral exploration, environmental studies, and geothermal exploration. They haven't actually done very much. So I don't know the answer to your question. The system that we used was developed in Denmark to map all of their groundwater. So they did that. So that's that's essentially what we did here, was map groundwater. And that's an important application that is being increasingly used across the US and other places. And they may end up doing repeat surveys in those kind of cases if the groundwater starts to dry up.
Yeah, no, I mean, that speaks to the temporal understanding across that period of time, provides insights, if you will. Yes, thank you.
Welcome.
Thanks for that question. We also have a question in the chat from Ivy Olberding. Do you know if there are correlations with other locations on Earth that have hot springs, for example, Iceland?
Yeah, they haven't done these kind of high resolution surveys, but in that example that I showed from Taupo, New Zealand, from the boreholes and from some regional geophysics, they inferred a similar kind of thing, right? Shallow freshwater aquifers and deeper fluids, but you don't really see the pathways. And there are local studies where you can see the same kind of thing. So it's not restricted to Yellowstone, certainly, but people just don't generally have this kind of data. I have it on tops of volcanoes because the hydrothermal alteration can post the landslide threat, and we can see similar kinds of things of layers of water layers in between lava flows. So yes, we have seen it, but most people don't have this kind of resolution of data to be able to image the pathways as clearly as we can.
Okay, are there any other questions? There is another question in the chat with regards to biodiversity. Is it similar underwater?
That's a good question, and I don't know, and I should, because there's been, well, actually, I don't know if people have looked at, yeah, they have. In Yellowstone Lake, yes, there is. What I'm thinking of, the black smokers in the ocean, and in Yellowstone Lake as well. There's quite a bit of biodiversity. I don't know if it's as extreme, but it could be, because in the case of Yellowstone Lake, it's the same situation where there's a lot of gases coming up, and there it's interacting with lake water. But I don't know whether it's as biodiverse as these other springs.
Okay, we have a question from Sark and Dressler. Has there been any age dating of the groundwater through isotope analysis? I'm curious how fast the groundwater moves through the system.
Yeah, it's a good question. Yeah, there's been tritium data taken in Norris, and so you can see tritium, so it's under 60 years old in Norris, in the Norris area. So that's the only age dating of the groundwater that I've seen. So it's obviously pretty young there, but I don't know otherwise.
Okay, Chris Wenzel's a little shy. He wants me to ask the question for him. Are there other remote sensing methods that you think would be nice to complement your existing study?
Well, certainly the magnetotelluric data that my colleague did just collect. It's really, we use the magnetic data, the susceptibility models to identify these clay layers, but it's not as, the resolution is not as good as magnetotellurics, and there's some more ambiguities that can occur in the magnetic data. For example, if they're reversely magnetized rocks, it might show up as looking kind of like a clay layer. So that's certainly one of them. Yeah, and follow-up studies by my colleagues, for example, my biology colleagues are going to go to this Firehole Meadows area where the resistivity data clearly show there should be hydrothermal fluids. And so they're going to look for, and it's a high elevation, so they would never have thought to look there. So there's that kind of thing. There have been some local shallow seeing geophysics, but I don't think, from my perspective, they really show a lot more than what we did. There's some cool studies where one of my colleagues is using the time domain EM data as a time series and near the geysers. So you can actually see the resistivity changes from going to higher resistivity to lower resistivity when the gases go through the geyser system. So you see the gas coming out, the geysers go up, and then the water comes back in the system. So that's kind of cool.
Thank you. Last call for questions. Anybody else?
Sounds like that might be it. Well, in that case, Dr. Finn, thank you so much for such a great, interesting, enriching presentation. Thank you to everybody who came out to make this a success. Really appreciate it from everyone. So thank you. And, you know, as far as I'm concerned, you know, hope to see you again soon. And again, Dr. Finn, thank you so much. That was great. Just great.
Thank you for inviting me, and have a good evening.
You too.